and we get ahead anyway, okay? So we've got a 0.5 chance of getting ahead the first time. We've also got a 0.5 chance of getting ahead the second time. Remember, the question says at least one. We've got at least one there. But we've had to toss it again. So luckily we've got ahead the second time. But we've got at least one. And remember, we multiply them. 0.5 times 0.5, which gives us 0.25. Let's say we toss the coin the first time, we get 0.5 here, ahead. We toss it again, but we get a tail. Well, that doesn't matter because we've still got a head here. So it's 0.5 for that head. We've had to toss it the second time. It's still a 0.5 chance because we've had to toss it twice. So it's a 0.25 chance. This one, we tossed the coin the first time, we've got a tail, 0.5. But then when we tossed it the second time, we got a head, which is also 0.5. So again, it's 0.5 for the tail, times 0.5 for the head, so it's 0.25. This time, we tossed the coin, we got a tail for the first time. We have to toss it again because it says 2 tosses the coin. But this time we've got a tail for the second time. So we haven't got a head. So we can ignore that bottom one because the head isn't involved in it. At least one head. Got one there. We ended up with 2 to be perfectly honest, but we got at least one. 0.5 times 0.5 because remember 2 tosses the coin. At least one head here, but we had to toss it again. There's a 0.5 chance of getting it again there. So 0.5, 0.5 for that one. The blue line, we tossed it the first time, we got a tails, but we have to toss it twice because it says 2 tosses of the coin. So we got a 0.5 head the second time, which is this one. But if this one, we've got a tail for the first toss and a tail for the second toss, there's no heads involved at all there, so that one doesn't count. So the overall probability of getting at least one head from 2 tosses of a coin is those 3 added together, 0.75, or a 75% chance. It's not easy with tosses of a coin because it's all 0.5s, but the key thing what I'm trying to get at is you follow the line, you follow the branch, you walk along the branch, yeah? So using this as your information, at least one head, yeah? But you've got to toss it the second time, so you've got to include these probabilities because you've got a 0.5 chance of getting another head, or you've got a 0.5 chance of getting a tail, but you've already got your one head there. But you've got to still do the 2 tosses of a coin. You can't stop there because, oh, I've got the toss of a coin, I've got my head, there it is, because you've only tossed the coin once. You have to toss it again. There's your 2 options. Same with this one, you tossed it the first time, you didn't get a head, but you had a 50-50 chance of getting it, a 0.5 chance, which is this one here. And then when you tossed it the second time, you had another 0.5 chance of getting it, which was here. So that's why that one is 0.5 times 0.5 as well. But this one, it's 0.5, but you didn't get a head. You just didn't get one at all. So you've not got any heads there. You've only got a tail. So that one doesn't count at all because you've no chance of getting a head in that particular. Does that make a little bit of sense? It's a bit clearer when you look at one that's not all 0.5s, to be perfectly honest. But that's how they work. That's how it works.
Probability is hard.
Yeah, these are a bit more tricky.
Fine up until now.
Yeah, these are a bit more tricky.
Yeah, we're practicing about trees and
So let's have a look at this. This one, these are a bit more tricky. So here's a tree diagram. This is John. He's a little bit unsure what he wants to wear. He's going out. Now he's got in his wardrobe, he's got a blue t-shirt and a black t-shirt. He's got some pink shorts and he's got some black pants. There's his pink shorts, there's his black pants. He can't decide what to wear. Yeah? So he's going to switch the lights off and he's just going to rummage in the wardrobe like this, okay? John picks some clothes at random from his wardrobe. What is the probability that he picks the black top and black pants? So the chance of him picking a black top is 0.6. It's a higher chance. It must be nearer the front of the wardrobe. He's got a bigger chance. He might have two of those, I don't know. But he has a 0.6 chance of picking the black top. He's also then got a 0.7 chance of picking the black shorts, the black pants. Yeah? So he's got 0.6 times 0.7. Does that make sense?
Yeah.
Yeah? 0.6 times 0.7. So there it is. There's the black top, 0.6. There's the black pants, 0.7. 0.42 is a 42% chance of picking those up.
I'll do it again.
Okay.
Could it not go the other way as well?
Yeah, yeah. So, no, because that's a blue top.
Also, because the arrow's not pointing to the...
Yeah, that's a blue top.
Okay.
He's picking a black top, black pants. Yeah? What is the probability he chooses a blue top and black pants? What's the probability he picks a blue top and black pants?
Is it 30%?
So he's got 0.4 blue top and 0.75 oops for the black pants. Yeah? 0.4 times 0.75 gives you 0.3 or a 30% chance. That's how they work. Yeah? That's how these particular questions work. Okay, what will happen in the exams at some point is maybe this, that you will get a picture like that, but you wouldn't see that, and it would say, oh, what's that missing number? You may not get that. Oh, what's that missing number? Yeah, it might give you a question where the numbers are missing. So you then think, well, this is the first event, blue top, black shirt. What's that missing number? It's going to be 0.4. Why? Because 0.4 plus 0.6 equals 1.
Yeah.
And then this section here, that event there, whether it's the pink shorts or the black pants, what's that missing number? It's going to be 0.25 because 0.25 plus 0.75 is 1. Because remember, adds up to 1, adds up to 1, adds up to 1. If all them little branches have got to add up to 1. Not one as a whole, but one per branch, if you will. Yeah, one per branch. Okay. So let's have a look at this example. And we'll build the tree in a second, and we'll do it on here. We'll build the tree. Let's get the light for that. So you're off to the soccer, and you like to be the goalkeeper. But that's going to depend on who is going to be the coach today. If the coach is Sam, then the probability of you being the goalkeeper is 0.5, 50-50 chance. If the coach is Alex, he doesn't think you're that good, the probability of you being the goalkeeper is 0.3, it's a bit less. Sam is the coach more often, 6 out of every 10 games, which as a decimal is 0.6. So what is the probability that you turn up to that football and you will be the coach today? Okay, so let's work it out. Let's work it out. So this is you. You turn up to the game. There are two options when you turn up to the game of who's going to be the coach. Yeah, who's going to be the coach? That's the first event. Who's going to be the coach? Now it could be Sam, or it could be Alex. They're the two options, okay? It says that Sam is the coach more often, about 6 out of every 10 games, which is a probability of 0.6, so that goes there. So what's the chance, what's the probability that Alex is going to be the coach?
0.4.
0.4. Right, because it adds up to 1. So you turn up to the game. If Sam's the coach, he's going to say yes or no to you being the goalkeeper. If you turn up to the game and Alex is the coach, is going to say yes or no to you being the goalkeeper. Okay? So we've halfway built our tree. If you turn up and Sam's the coach, the probability of you being the goalkeeper is 0.5. So the probability of you not being the goalkeeper is also 0.5, because 0.5 plus 0.5 is 1. If you turn up to the game and Alex is the coach, the probability of you being the goalkeeper is 0.3. So what's the probability of you not being the goalkeeper?
1.7.
0.7. There you go. So now let's look at our scenario. You're going to turn up to the game. What is the probability that you turn up to the game and you are the goalkeeper today? What's the probability? Well, you could turn up to the game and Sam's the coach. Hiya Sam, can I be in the goals? Go on then. 0.6, because it's Sam who's the coach, times 0.5, which gives you 0.30. You could turn up to the game and Alex is the coach. Hello Alex, can I be the goalkeeper today? Yes. 0.4 because it's Alex, times 0.3 because he doesn't think you're that good in the goals. 0.12. So there are your two options, your two chances. If you turn up to the game, Sam's the coach and he says yes, you're the goalkeeper. Or you turn up to the game and Alex is the coach and he says yes, you are the goalkeeper. So there are your two options. So the overall probability is 0.30 if it's Sam, 0.12 if it's Alex, so the overall chance of you being the goalkeeper is 0.42, or a 42% chance. Does that make sense? Yeah? Does that make sense?
What if you just times the two yes numbers? Would that be wrong?
What do you mean the two yes numbers?
That
The,
what it says.
the 0.5 times the 0.3?
Yeah.
Because you've not took into account the first chance, the first option of who's going to be the coach.
Okay.
Yeah? So what you've got to do, you've got to kind of play these out as little scenarios. That you've turned up to the game, oh it's Sam, and Sam says I can go in the goals. It's Sam, 0.6, and he says 0.5, you can get in the goals. Or you turn up to the game, you get out of the car and it's Alex. Alex don't think I'm that good. He's not the coach as often as Sam. Sam's the coach 6 out of 10 games, Alex is the coach 4 out of 10 games. I've turned up on a game when Alex is the coach. He doesn't think I'm that good. What's the chance of me going in goals? It's a 0.3 chance. You don't think you're go on get in the goals then, yeah? But overall scenario is that you've turned up to the game, there's going to be a coach, and they're going to say yes to you. But the overall chance, depending on who the coach is, so it's 42% because you add the two together. It's a bit confusing because you're multiplying these two, but then you're adding those two. Now a lot of the times in the exam you'll just get one option. Yeah? It might not say what's the overall chance of you being the coach today. It might say to you, what's the chance of you turning up to the game and Alex is the coach and he says yes, then it would just be 0.12 because it's focusing just on him being the coach. Yeah? So just be careful of the wording of the questions because these aren't terribly difficult. It's the wording of the questions that they'll try to trip you up on. So what's the probability you're going to the football? Alex is the coach and he says you can be the goalkeeper. Alex is the coach, 0.4. He says you can be the goalkeeper, 0.3. So the answer is 0.12. What's the probability to turn up to the game? Sam being the coach and him saying no, you're not going in the goals. What would that probability be?
58%.
How many?
Oh, sorry, 58.
It'd be
Oh, you mean
0.6 times 0.5.
Oh, I went to the whole
Yeah?
total.
Because you've turned up to the game, Sam's the coach and he says no. 0.6 times 0.5. It'd be the same. Yeah, it'd be the same percentage of that. That's how these work. Yeah? So just take a bit of time reading them when you see these as a question. Just take a little bit of time
Would you have to draw a tree like that in the
You
exam?
very rare you'd have to draw one. Very rare you'd have to draw one. So this kind of thing just goes through me being the drawing. There it is, there's your options, so it's a 42% chance. Sam here plays cricket, he bowls overarm and underarm. The batsman can be either bowled out or caught out. If Samir bowls overarm, the probability of the batsman being run out is 0.65. If Samir bowls underarm, the probability of the batsman being caught is 0.15. Samir bowls overarm 85% of the time. What is the probability that the batsman is caught out from an overarm ball? Wow, there's a lot of information going on there, isn't there? Yeah? So let's practice it on here. Let's practice drawing this on here. So this isn't about goalkeepers anymore, it's about cricket now. You don't need to know anything about cricket. Let's have a look. So there's our first event. Overarm or underarm. Yeah, because that's where he bowls, overarm or underarm. Okay. The second option is batsman being caught, or what's the other one? Run out. So obviously it's the same options. So we're building ourselves a little tree. Samir bowls overarm 80% of the time. Overarm 80%, 0.2?
Not for
No?
0.8.
0.8, yeah, of course. 0.2 is the other one, isn't it? Yeah? Underarm is 0.2 because it makes 10. Why have I changed it to a decimal? Because these two are in decimals. So if Samir bowls overarm, the probability of the batsman being run out is 0.65. What's the probability of the batsman being caught?
0.35.
We've now completed the top half of the tree. Let's do the bottom half of the tree. If Samir bowls underarm, the probability of the batsman being caught is 0.15. Caught, 0.15. So what's the probability of him being run out?
0.85.
Boom, there's the tree. We've done the tree. Yeah? Now at first glance, when you first read that, you'll have thought to yourself, what in God's name's going on here? Yeah? But once you then break it down to the overarm, underarm, caught, run out, yeah? Then you can start to work this out. And like I said, more times than not, this is given to you, but with a couple of missing numbers. You just have to fill the missing numbers in. What is the probability that the batsman, is caught from an overarm ball? Caught from an overarm ball. What's the probability?
20%.
0.8 for overarm.
Times 0.35.
Times caught out. That's it. That's the answer. 0.8 times 0.35, which is?
0.28.
Or the 28% chance. So, very rare that you'll have to build one of these in your exam paper. Very rare. They normally give it to you, but with a couple of numbers missing. Let's check if we've got the right answer there. 28%. Yeah? So it's pretty rare that they will give you one to build. But we just built those last couple because I wanted just to show you how it works and how you can how you get those particular numbers. Employees at a company were recently asked whether they cycled to work or drove to work. 82% of the workforce are under 40 and 40% of those drive. Of the workers aged over 40, 73% of those drive. The manager of a company decides to reward an employee with a brand new bike. What is the probability of the boss choosing an employee over 40 who cycles to work? Oh my gosh. We could do ourselves a little treat, couldn't we? Yeah, we could do ourselves a little treat. Or, just by using those numbers, we could kind of work it out without drawing a tree. But to me, drawing a tree would be easier. Yeah. So let's get a tree going. Let's get a little tree going. So I'm just going to remove these overarms, underarms, courts and run-outs. Here we go. Let's redraw this little. So what are our options? We've got under 40 and over 40, haven't we? For our first two options. Under 40 and over 40. Okay. 82% of the workforce are under 40. 82%. So 0.82. Yeah. That's this line here. 82% of the workforce are under 40. And 40% of these drive to work. So what have we got here? We've got cycle and drive, haven't we? %, 0.4. Of the workers aged over 40, 73% of those drive to work, 0.73. There we go, that's the information we've got from that question. Yeah? We've got some workers that are under 40, some workers that are over 40. And they either cycle or drive, cycle or drive. 82% of the workforce are under 40, that's 0.82. And 40%, 0.4, cycle to work. Of the workers aged over 40, 73% drive to work, 0.73. Okay? We've got some missing numbers. Let's start putting the missing numbers in first. What's this missing number down here? What percentage of the workforce are over 40? Yeah? What percentage of the under 40s drive to work as a decimal?
0.6.
What about the over 40s? How many cycle to work?
0.27.
Boom, we've just finished the tree. The tree's done. Okay? The tree's done. Now we can answer the question. The manager decides to reward an employee with a brand new bike. What is the probability of the boss choosing an employee who is over 40 and who cycles to work? Where am I going with my red pen? Am I going up or down?
Down.
Where am I going now?
Up.
Yeah, over 40 cycles to work. 0.18 times 0.27.
We'll just be a calculator.
Yeah. So let's have a look what the answer is. 4.86, so 5% of the workforce. You have a 5% chance of getting a bike. Yeah, a brand new bike. That's why he's gone down that route, because the smallest numbers. Yeah. He's not gone over 40 who drive to work, has he? Because there would have been more chance of giving a bike away. Yeah, not daft, is he? But that's how they work. That's how these work. You might have been given all that information, apart from the blue numbers. You would have had to put them in, and then you would have had to answer the question. But I'm just pre-empting you that if you do get a question that looks like that, you can draw a tree by using this information. But what you've got to do is you've got to look at it as not a whole thing, but as this little bit first. Then there's that little bit. So you've got workers that are under 40 and over 40. That's your first branch. Cycle to work, drive to work, cycle to work, drive to work. Yeah, that's how you've got to kind of look at these particular questions. So far so good. We'll have a go at a few then now in the workbook. Yeah, because we've got a couple of questions still to do there, but there's one I want to draw your attention to in a few minutes. So in the workbook now, you've got questions here at the front with the answers there, but what I want to focus on, if possible, are these questions at the back, because they're exam style questions. Okay. No, I'll tell you what, have a go at this one first. There's a tree. There's a tree. Okay, it's next to the back page, next to the one that you've already done at the back. So it's the next one backwards, if you will, or coming more forward. So have a go at that one, it's the...
Keep going down.
Yeah, so keep going and you'll come across the tree. See if you can finish that one. The probability of selecting a car owner by the age and the type of car that they have. Complete the probability tree. Work out the probability that this person under 30 has got an electric car. So you should have some missing numbers to fill in. Yeah. What's that worth in total? 4 marks in total, you see. 2 for that filling in and 2 for the little working out at the bottom. So it's a 4 mark quiz. That's a nice straightforward 4 marks question.
I'll take that.
Have we got 12? 0.12 or 12%? Yeah. So yeah, 0.7 times 0. Oh, sorry, there you're missing numbers. So the question is under 30, 0.3, electric car.
It's an easy thing, isn't it?
It's an easy question, though, isn't it? It's an easy question.
Yeah.
Let's go. Keep coming towards the front of the booklet, and you're going to come to a travel agency shows some information about 60 holidays bought by customers at a travel agency. Okay. Now this question is a 6 marker. Okay. For 2 marks, complete the table above. So complete that table now. This is a 6 mark question. So just back one more page towards the front of the book.
Oh,
You see it there? It's about holidays.
yeah.
Yeah.
Just that one page.
That's it, yeah.
Where we were.
Let's look.
16.
Yeah, so keep going back. Keep going. No, keep going, sorry. Nice mistake there. This one here, yeah? So you're going to complete that table first. Again, this is a calculated question. It's a 6 mark question. Once you've completed the table, the next 2 questions are on the next page. Now think back with this one. Think back to the flower shop question. Think back to Jane in the flower shop. Remember, the first part of the question was every flower. The second part of the question was a little bit more specific. So fill the boxes in first. I think we've got this one on the big screen actually. is. That's it on the big screen. We'll go through the answers to this one in a few minutes. Nice easy start there, the boxes in. 2 easy marks. But then it gets a bit more tricky. Interesting. That's all you've got for your first
Oh,
answer.
it's tricky, isn't it?
So that's
I don't know what I'm doing.
so that's right. Yeah.
That's right, next
Yeah.
one is that.
That'll go a bit more, bit simpler, won't it?
Mm, yeah,
Yeah.
get there eventually.
And it's this bit. That's the tricky bit.
Oh.
That's the tricky bit. Think about the wording of the question for that bit. You on the table, Elizabeth? Yeah, the questions are on the other side now. The questions are there. 2 questions, yeah? First question is relatively straightforward. The second question is a bit trickier. We'll go through the second part of the question in a minute. It's a tough one, that, isn't it, that second
Is it
part?
right one?
Right, it's nearly. You've got that number right. You've got the bottom number. You've got the bottom number wrong. But you're nearly there. We'll go through it as a team in a second. It's a difficult, tricky question. This is the first part. Let's see if anyone can get that second part of it. We've got a big answer there. Yeah, we've got an answer there on that side. We'll check whether it's right in a second. It is tricky, this second part of the question. Part number three, sorry. This question.
I really don't like the ones where you have to explain.
Yeah,
I just
it's
think,
tricky, isn't it?
oh,
It's tricky.
yeah.
Let's fill the table. Let's do the table. Let's get question number 1 out of the way first. Let's complete the table. I think we've all got this. So I did the 26 there. I did 60 minus 34 to give me 26. When I'm doing this, I always do make it easy for myself. So I just add those 2 numbers together to give me this missing number here. Yeah? 32. Yeah? I can easily find that number now because I've got 23 take away 10. It's going to give me 13. Everything's looking good now. Now I could either 26 minus 14 minus 10 to give me this number, or I could do 60 minus 32 minus 23 to give me that other number. Doesn't particularly matter which rear end I do it, so I've got a 5 there, so that means I've got a 2 there. Yeah? So that's my table completed. Now I'm guessing that you've all got that. Yeah, I'm guessing you've all got that. So we're getting to the questions. These are the tricky worded questions. I think you've all got this one. A customer who bought a holiday is chosen at random. What is the probability that this customer bought an all-inclusive holiday for a couple? So your key word here at the beginning is this. A customer who bought a holiday is chosen at random. 60 people went into that travel agent to buy a holiday. 60 people. So 60 is your bottom number. What is the probability that the customer bought an all-inclusive for a couple?
18.
18. So 18 out of those 60 people that went into that travel agency bought all-inclusive for couples. Simplified, 3 over 10? 3 over 10. Yeah, 3 over 10. 18 over 60. Oh, I'll give you the answer. Oh, it's 3 over 10. This bit now is the more tricky bit. The travel agent says, of the couples and families who bought holidays, the couples were more likely to have bought an all-inclusive holiday. Now this is focusing on 2 things. It's focusing on the couples and it's focusing on the families. Okay? So, 2 sums. The couples first. How many couples bought holidays in that shop? 34. How many of those were all inclusive? 18 out of 34. Families next. How many families bought holidays in that shop?
26.
And how many of those were all inclusive?
14.
So, remember what I said right at the beginning of the lesson? That probabilities are either fractions, decimals or percentages. Yeah? We've got fractions there in our answer. Purely and simply because that's the way the question's set up. It's made us have fractions of our answers. We know from past maths experiences how difficult it is to compare fractions because we've got to make the bottom numbers the same. Well, look at those fractions. I can't think of a bottom number that's the same as that I can make the 34 and the 26 into. So what am I going to do? I'm going to change them. And I'm going to change them both to percentages. And that way I can do the comparison to see whether more couples bought holidays or more families bought holidays. Because that's what the question says. The couples were more likely to have bought an all-inclusive. Well, let's see if the travel agent's correct. So we're going to change this to a percentage. How do we do that? Well, we do 18 divided by 34, because that's what that means, 18 divided by 34, times by 100. What does that give us as a percentage?
52.9.
52.9%. So we can round that up to 53, because it's virtually 53%, yeah? Let's do the same thing for the families, but this time it's 14 divided by 26 times by 100. What does that give us?
53.8.
53.8%. So we could round that up to 54, couldn't we? Because it's pretty close to 54. So the travel agent says, of all the families and couples who bought holidays, the couples were more likely to have bought an all-inclusive. Is it correct?
No.
No. 53% bought all-inclusive as couple, 54 as family. So that part of the question, that second part of the question here, this number 3 part, that was tricky. Yeah, that was tricky. So, again, easy to fill in. Yeah. Fairly easy to do. A little bit more difficult, takes a bit more thinking about. It's a 6-mark question, that. You definitely get 2 for filling that in, and you would probably get 2 for that answer. But this is the tricky part of the question. And again, it focused specifically on couples and families. So the key words to look out for when you're reading the questions are, if the question says somebody's picked at random, it means everybody. If it's specific, couples, families, then that's all you focus on. You just focus on the couples, or you just focus on the families, obviously depending on what it's talking about or what it's saying to you. So that's important. It's important to remember that and be able to pick that up out of the questions. Again, it's not, the sums are, on a calculator, the sums are straightforward. It's what sum do I need to do. Yeah, what sum do I need to do. Do you understand that one? Yeah? It's tricky, isn't it? It's just a bit tricky, the wording of the question. So, we're just going to carry on working backwards through the book to get to number 8. Okay? It's a probability question, number 8. Now it's a bit like our guy that was going to give his employee a bike or something like that. It's a similar kind of question. Yeah, I've not got it on the big screen, but I need to put it on the big screen. Benji sells items in a shop and online. In a survey, he asked 100 people if they prefer to buy items in a shop or online. And the people are aged under 25, 25 to 40, or over 40. 56 of the 100 people prefer to buy online, 27 of the people aged under 25 prefer to buy online, and 12 of the 33 people aged 25 to 40 prefer to buy in a shop. Of the people aged over 40, 8 prefer to buy online and 17 prefer to buy in a shop. Wow, there's a lot of information there, isn't there? Yeah, and it doesn't make much sense. It doesn't make much sense. So we're going to build one of these. That's what we're going to do. So we're going to look at, first of all, the 2 options. He's got an online shop and he's got a physical shop. Okay, so there are the 2 options of where people can buy goods. So the people that come shopping in his, either online or in his shop, they're under, what are they, under 25? Yeah. Under 25, so that's going to go here. 25 to 40s, they're going to go there. And finally the 40 plus the over 40s are going to go at the end. Or not at the end rather, because total is going to go at the end. So all we're doing here, we are building our own little probability table. And again, building the table is relatively easy once we can understand what goes where. So that's what our table is going to start to look like. Okay, we're just going to pop some numbers in there in a second, because all the numbers are given to us. And once we get all the numbers in, the question will become relatively simple. The hardest bit of this is building the table. In a survey, he asked 100 people. There you go, 100 people. There's the total number of people he's asked. 100. 56 of these prefer to buy online. Where am I going to put that 56 then?
In the top right, yeah.
There?
Yeah.
Top right? Yeah. Because 56 out of those 100 prefer to buy online. 27 of the people aged under 25 prefer to buy online. So 27 people that are under 25 want to buy online. So where's the 27 going?
First box there.
Under 25 prefer to buy online. It's a two-way table. 12 of the 33 people aged 25 to 40 prefer to buy in a shop. 2 bits of information in that question. 12 of the 33 people 25 to 40. So that means there are 33 people 25 to 40. So that's going to go there, isn't it? And it said 12 of them prefer to buy in a shop. We're just missing some information in this final corner, so let's do this. Of the people aged over 40, so in this column, 8 prefer to buy online and 17 in a shop. Of the people aged, one person who prefers to buy in a shop is chosen at random to win a prize. What's the probability that this person is aged under 25? Okay, well, we need to fill the table in first. Yeah, we need to fill that table in. Right, let's crack on and fill it in. Let's get a different colour pen then. Right, okay, so it's up to you which way you start to fill this in. Me, I always start at this far side and work my way back. Don't ask me why, but I always do. 44. 8 plus 17.
25.